Well, I don't know either. Also, I wonder if any one person in the world is watching this. There was some semi-official meeting, whatever, 10 days ago, and then I sent out the notes by Irina. So you are aware of this. So we can start where we stopped 10 days ago. Yeah. Okay. And where did we stop? We considered the whole algebra. Well, H of Q. Okay, so it was isomorphic to, or equal to the split K group of representations of Q, but with certain product, whole product. Or maybe, how should I say this? Maybe I should say, I don't know. No, maybe I shouldn't say this. Sorry. Okay. And we maybe computed a few examples, like for A2 quiver. Like this. Okay, so we computed that this product was the direct sum of those, and V3V1 was V3 plus V1, and V3 product V2 was V3 plus V2. And this was because I chose some specific order. In general, there is a preferred order in which the products are just direct sums with coefficients 1. Or maybe, well, I should say this. Something like this. And then we also proved that the whole algebra. Well, it is a module over polynomials in Q. Q is the cardinality of our finite field. Or I don't know how to say this. Maybe I should say like this. And if I fix my ground field, then this is the specialization of well, this was not a proposition but a theorem, and we didn't prove it. But I almost explained that h of q tensor over polynomials with the fraction field is generated by the classes of simple modules SI. Okay, so this was the contents of the last time. And now the only thing which remains is a very straightforward computation like this. So, well, lemma. So if I have sorry. Yeah. So if I have two neighboring vertices, then I will have certain relation between two simple modules. So it's I, it's J, just the names of vertices. And then if I take the class of Si, multiply it with Sj, with Si, then I will have sort of Serre relation. Si, Sj, Si. Sorry, it was I, J, then I, J, I, and then J, I, then this will be 0. So this is a cubic relation. Which is reminiscent of the Serre relation. And we will return to this reminiscence. But let's first check it. Maybe somebody will volunteer to check it. I mean, just compute explicitly something we already know. For example, we know what is Si times Sj, right? It was computed over there. This is the class of Si direct sum Sj, right? And now we want to multiply this by Sj. So what will happen? We'll take this semi-simple module, multiply it with Sj, and what happens? So as Sj is in the is a sub, and the quotient is this, right? So this will be a sub, like this. Then there will be something, and then the quotient will be like this. So let's so the question is, what can possibly occur here, and then what are the possible coefficients? Okay, well, it's ij, but it's always ij, so maybe we can forget about it. And so, as Misha says, one possibility is k goes to k plus k, but by the zero map. Okay, and what is the coefficient of this? No, how do you mean? So how many submodels of this sort you can find in here such that the quotient is of this sort? Yeah. Yes. Any line in here will suffice. So the coefficient is q plus 1. Okay. And another possibility is what? Yes, I also think that this is the only possibility. Because if in the quotient you have yeah. Pardon me? So we are computing this. Uh-huh. Okay, so this is, well, this is V3, right? And this is V1 plus V2. No, V1 plus V3. Okay. So you say that it's possible that we have a non-zero map like this, embedding into k plus k. Okay, and then we choose such a submodule. Right, it can happen, right? Because if we choose this k to be the image of this embedding, right, then we will be in business. So the coefficient will be 1. Right, if we choose this submodule, this k in this line in this plane to be the image of this embedding, then the quotient will be the zero morphism. So it's the only possibility, right? We must choose this line to be the image of this embedding. No other choice will give such an exact sequence. Right? Are you dissatisfied or? Okay. Now let's compute the second sum. So once again, we know what is Si times Sj. So we want to compute Si plus Sj multiplied by Si on the left. So we have the opposite exact sequence. K goes to K, goes to something, goes to 0 to K. So what can this something possibly be?
So
yes. we compute this product here. This is the answer. So this must be a submodule.
I'm sorry, can you read the formula above? Because I think I can't distinguish between your i's and j's in the formula of this book.
Ah, sorry. It's IIJ. J, I, J, I, and J, I, I. The first summoned. Oh, sorry. This was stupid. I didn't want this, right? I wanted. Sorry. Yeah, I wanted this. Yeah. Okay, so then we erase everything. And start afresh. So we'll have k goes to 0, to something, to k goes to k, like this. And the question is, what is this something? Yes, so now it's k squared goes by 0 to k with coefficient q plus 1. But not necessarily. Yeah, you can also have a non-trivial map here, and then this k can lie in the kernel. The quotient, yeah, then the quotient will be not 0, right? So just this. Okay, and now here. Si, yeah, k to 0, right. So, what are the possibilities? So the semi-simple case is, again, k squared goes to k by 0. And how many possibilities like this? Again, q plus 1, right? And also, k squared goes onto k with coefficient 1. Right? And finally, what do we want to compute? Sj Si. No, not quite. Yeah. Did I? I don't think so. So first, maybe Si times Si is just again q plus 1 times k squared to 0, the class of this. Yeah. And so we will have submodule k squared goes to 0, to something, to Sj, so 0 to k, right? And what are the possibilities here? So just k squared goes by 0 to k with coefficient 1, right? But there was this q plus 1, so altogether we have right? So now let's no? See what we get. The coefficient, say, of this module is q plus 1 from the first. Oops.
No, it's IGI, it's the second. I think
Si times Sj.
no, there should be additional sum there. We computed it the last time.
Aha.
We had V1 and V3.
Okay. So this is
In this, from this, there should be another module there where there is isomorphism. Because like this, the formula is not at all.
So V2 is an isomorphism, yeah? But
So it should be V1 plus V3 plus V2. I mean the class of V1 plus V3 and plus class of V2.
which one you are computing?
Product of V1 and V3 is the class.
V1 and V3. So here we did not compute it, right?
Is the class of this sum plus the class of V2. So
Okay, so this is correct, but also V1 times V3 is V3 plus V1 plus V2.
So we should have change SI times Sj into sum, and we should have changed Sj times Si to this in our computation. So to make them simpler, just change Sj times Si.
Okay. So what do we have to change? Everything. Okay. So okay, I want to multiply this by Si on the left, for example, yeah?
And on the right, also
Okay. And then it will be in the opposite direction, yeah? Pardon me? It's the second product. Yeah, this one. Okay, so this way. No, okay. And well, let's then multiply it on the other side, like this, yeah. IJI. And then it'll be just this. And we know the answer. This is JII. Yes, JII. Okay. This will also. What did we not compute? This one. Yeah. Yeah. So SI times I times J.
This is IJI.
Mm-hmm. And what is easy? J times I is easy. So this is as J times S I plus S J. And here you will have 0 to K. Yeah? No? Yes?
And how it could turn out into SJ times something?
It's SI times this, right?
The calculation was correct.
Yeah, it was. You changed this.
Mm-hmm.
You just need to calculate SI, SI is J.
You were right. There should be K to 0, not 0 to K there, because the factor is SI. It was right here before you changed it.
So we only have to compute this, right?
Replace 0K to K0 this here. Because it should be SI.
Mm-hmm. So it remains to compute SI, SI, SJ. But we know SI times SI. So it's Q plus 1 times K squared to 0. Times this. And it's in the opposite direction. 0 to K. K squared to 0. Okay. So it can be K goes to 0. What is the coefficient? K squared to K. What is the coefficient? Yeah, the coefficient can be only 1. And also K squared surjects onto K. Just because it has the unique submodule like this, right? And this also has a unique submodule like this. So coefficient is 1 again. Okay, so now let's check the proposed relation. Either y iij, it's here. JII.
We have this q times q plus 1, and it's
So maybe it should be the opposite. Maybe we should multiply q here. No. Yeah, so we just put q here, not there, yeah? JII is,
just write down the explicit what we have. I mean, all the sums.
yeah, JII is here. It has q plus 1, this module. Yeah? So if multiply it by q,
It will be q squared plus q.
q squared plus q. And this is and from the first one, iij, extra 1. So it checks, yeah? Yeah, so I think it checks. Yeah.
No, because look, q squared goes to 3 when it's surjective. We have in iij.
Let's compute the coefficients here. Yeah, of this. So iij is 1.
No, q plus 1 because we have q plus 1.
Yeah, okay. So q plus 1, q plus 1. Mm-hmm. Okay, so finally it worked. Congratulations. And now the last minor trick. Is as follows. Twisting. So, well, first of all, we change the scalars a little bit to the Laurent polynomials in square root of q. So H prime will be our whole algebra with extended scalars. And the new multiplication is dot multiplication. It is the old whole multiplication with certain power of v, namely we take the dimension of v, dimension of w, and their Euler form. So recall that the dimension of v well, is an element of the usual Grothendieck group of representations of Q. So it is z to the power number of vertices. Well, actually, dimension is positive. Of dimension of an actual representation is positive. And then the Euler form of two classes, but well, maybe it's a maybe wrong idea. I should say dim V, dim W, because in brackets I usually denote the class in the split Grothendieck group, but we have also projection from the split Grothendieck group to the usual Grothendieck group. So this is just dimension of home from V to W minus dimension of X1 from V to W, and there are no higher X. So this is just the Euler characteristic of homes. And that's why it's called Euler form. Okay, and then corollary of what we just proved is that if there is an arrow, so the Cartan matrix coefficient Cij is -1, then Si to the divided square times Sj minus Si Sj Si plus Sj Si divided square is 0. So it's the usual Serre relation, but quantum. And here the divided power, Si divided power, is the usual square divided by V plus V inverse. Okay, so that's it. That's how Ringel, 30-something years ago, rediscovered the quantum group in the whole algebra of ADE quivers. In fact, you can apply this to arbitrary quivers, not necessarily ADE. But then the corresponding Lie algebra will be infinite dimensional, so-called Kac-Moody Lie algebra, but it has the same quantization, Kac-Moody quantum group. And that's all I wanted to say about the whole algebras. So the main message is that before we studied the whole algebra for the Jordan quiver, and it was a commutative and, well, very important, ubiquitous algebra, but commutative for some random reasons. So if you consider more general quivers, then the algebra is not commutative anymore, but it's, again, very important. So if Drinfeld had not discovered quantum groups from the statistical physics considerations, then it would be discovered just 5 or 10 years later this way from the whole algebras of quivers. Okay. And also, as I mentioned, what we're really considering is the, well, for each dimension V underline, we can consider the vector space E of EV, such that direct sum over all arrows like this, L of VI's over all vertices. And there are finitely many orbits, and the orbits classify the representations of this total dimension. Okay, you know that there are finitely many indecomposables, so finitely many representations of each. We are just multiplying. Well, the whole algebra is the way to multiply invariant functions on this space. And now this classification of orbit does not depend on the ground field, but the multiplication does depend, because you need to integrate over fibers, so you need to count the points in the fibers. If your field is finite, then there is a finite count. They will have some cell decomposition, and from this cell decomposition, you also can introduce this Q as an abstract variable. Okay, but now the standard basis in our whole algebra is the basis of characteristic functions, just 1 at some orbit, 0 everywhere else. And this corresponds to the Poincaré-Bergov-Witt basis of the quantum universal algebra. But now using homology sheaves and their Frobenius traces, the same thing we did for affine Grassmannians to produce Schur functions in place of whole Littlewood polynomials. And now these analogs of Schur functions will give rise to so-called canonical basis of the quantum universal algebra. It's called canonical because it's independent of choices. I mean, there is only one algebra, like universal algebra of the group, whatever, E8. Okay, so all these algebras will be isomorphic to this. Well, all the twisted algebras will be isomorphic to the same thing, as we just proved, essentially. But they are different algebras with different realization. And in particular, the standard basis, like PBW basis, like, for example, you can take, in this A2 example, you can consider like the generator, whatever, S1 Si Sj minus Q Sj Si. Si minus Q Si Sj. Yeah? So this is the choice for such orientation, and this is the choice for the opposite orientation. And these are different elements. Okay, so already for the next root vector, there are two different choices. And they're really different. Okay, but if you consider those Frobenius traces by orientations of the underlying Dynkin graph, but there is just unique canonical basis. It is independent of any choices. Well, that's a theorem of Lustig, but that's a fact. And that's why it's called canonical. It is also very dimensional representation. Then you can act by this algebra on the lowest weight vector, and so it surjects onto any finite dimensional representation, just by the action on the lowest weight vector. And then this canonical basis is very well adapted to such surjections. Namely, most elements of the canonical basis will project to 0 here, just to 0. But those that do not project to 0, they will form a basis in here. So either they go to 0, or the remaining ones are linearly independent and produce a basis here. So this canonical basis is just a wonderful thing. It also simultaneously produces the basis, the canonical basis, in all the finite dimensional reducible representations. And there are many more wonderful properties of this canonical basis. So I strongly advertise this. Okay, so now we are done, and let's start the representation theory over p-adic field. Well, let's start right away with the V representation. But now it will not split, so it will be not symplectic group, but twofold cover metaplectic group. The kernel, the center will be just twofold. Okay, and well, if you remember what we did over the finite field, somehow the most non-trivial part was the Fourier transform. So we wrote down, well, the general ideology is just the same. You start with a representation of Heisenberg algebra. There is a unique representation by Stone von Neumann theorem. And now the symplectic group acts by automorphisms of the Heisenberg group. And so it must act on this unique irreducible representation projectively. And we obtain a representation of some projective representation of a symplectic group that is representation of its central extension by say, by the circle S1, because this representation is unitary. I mean, the Heisenberg irreducible representation is unitary, and those intertwining operators from symplectic group, they preserve the unitary structure. And it can be written down explicitly just by very similar formulas, and we will do this next time. But the most interesting formulas involve Fourier transform. Like if you take some matrix like this, 1, -1, then this will act by Fourier transform. And so we need to study Fourier transform. And the Fourier transform in p-adic situation is a little bit more delicate than in the finite field situation, because somehow what you apply it to. Well, the main, the key computation will be Fourier transform of some Gaussian function phi a that we did for finite field, but it's well, it's a function, and you cannot apply Fourier transform just to all functions, just because it involves some integral, and this integral over p-adic field in general may diverge. So the standard way out is you apply it to L2 functions, and then you check that Fourier transform preserves L2. But L2 functions, they are only classes of functions. Yeah, so you cannot take value at any particular point. Yeah, for L2. You know this. So it's not very convenient to our applications. And another good space of functions is Schwarz functions, rapidly decaying functions. And then they are preserved by Fourier transform. That's the standard fact from the real analysis. And the same holds for p-adic situation. So I will start by explaining this. Well, so we need the additive character psi from our field to the additive group of, sorry, to the multiplicative group, from the additive group of p-adic field to the multiplicative group of complex numbers. And what is this? Well, it factors through the quotient QP modulo ZP, so it's trivial on the periodic integers. And QP modulo ZP, it is the same as a, well, it embeds into Q modulo Z. How does it embed? Well, you can take Z and localize it at P, and well, take quotient modulo Z. So there is such an equality, and it embeds here. Okay, and finally, in here you have a very standard character, exponent 2 pi I x. And that's our character psi. Okay. Now also we will need a Haar measure on our field, say K of periodic numbers. So it's a measure which is invariant under translations, such that the integral, well, the whole field has infinite volume, but it has maximal compact subgroup of periodic integers, and the integral over this maximal compact subgroup is normalized to be 1. So it's our choice of Haar measure. Then it's uniquely defined by this. And for example, it implies that the integral over the maximal ideal P of dx is what? Right. Just because the whole ring of periodic integers is the disjoint union of p balls of radius 1 over p, and they're just shifts of which translates of each other. By definition of Haar measure, their integrals are the same, and they add up to 1. So each one must be equal to 1 over p. And now the main definition is yes, yes. Yes, that's what we're going to do. We're going to integrate over k. That's why we need this Haar measure on k. But the integral over constant function 1 is divergent. But we will do integrals for better functions, so the integrals will converge. So the Schwarz space S of k is the space of locally constant, compactly supported functions from k to complex numbers. Okay, and well, you see that they are indeed rapidly decreasing, and even very rapidly decreasing. They're compactly supported, and also the standard. Well, the only. Well, if you think of what are the continuous functions on totally disconnected field to complex numbers, they must be locally constant. Okay, so we can consider continuous functions rapidly decay. They must be locally constant, and we define them as compactly supported. Okay. Now, then we will prove soon that this space is preserved by the Fourier transform, just as in the real case. But as we will do some computations, you will see that as opposed to, well, due to this locally constant and maybe compact support condition, this function only assumes finitely many values. And all the computations are very much like over a finite field. They are actually finite sums. So this analysis, this Fourier analysis, is some mock version of the real Fourier analysis. There are essentially no estimates, just some finite sums. So maybe here we introduce some topology on the Schwarz space. So let's say that a sequence of functions converges if there is a finite dimensional subspace say V in the Schwarz space S of k containing all the elements of this sequence and their limit. And in this finite dimensional subspace, there is the standard notion of convergence. Just, okay. Now the dual space S prime of k is the space of all C-linear functionals S of k to C. And with this notion of convergence, they are continuous. So usually in the functional analysis, you have some space of test functions and with some topology, and then you consider all the continuous functionals in this space. These are distributions or generalized functions. Okay, and here this topology is so primitive that all the functionals are necessarily continuous. Okay, now we have an embedding of functions into generalized functions. In this particular case, Schwarz space into the space of distributions. A function f goes to distribution lambda f, and the lambda f evaluated at another function f prime by definition is the integral over k of their product, f of x, f prime of x, dx. So this integral clearly converges because both f and x and f prime of x are compactly supported, right? So it makes sense. So we have such an embedding. And this is the standard way, again, in the functional analysis, if you had any experience, didn't you? No? You have had? Representation theorem. Okay. Okay. And now finally we define the Fourier transform of a function is the integral of psi of xy, f of y, dy, and well, this integral converges again for the same reason, because f of y has compact support. So this number is defined. This function is defined, but this function could in principle could be bad. Say not compactly supported or whatever, but in fact, it is quite the opposite. The Fourier transform of the Schwarz space again lies in the Schwarz space, and the proof is very straightforward. Namely, well, somehow Schwarz space is spanned by just the characteristic functions of some balls, say chi, the characteristic function of the ball A plus p to some power n. Okay, and then you know that, well, just by this formula, immediately you see that the translations give rise to multiplications by some characters, and multiplications, again, the dilations give rise to dilations here. So it suffices just to consider the characteristic function of the ring of integers. So since translations, well, Fourier transform of f of x plus a is Fourier transform of f times psi of a, and Fourier transform of f of whatever c times x is Fourier transform of f of c inverse x, something like this. It suffices to check that the integral, well, the Fourier transform of the characteristic function of O is itself. Okay, and well, any volunteers to check this? Well, it is related to the fact that the conductor of psi is O. It means that the set of elements x such that psi of xy is 1 for any y in O, this is O again. So to say, the orthogonal complement to O is O itself. O is self-orthogonal. Yeah? This is clear. And this immediately implies that just because if you, as I said, the integral is really a finite sum. But if you sum up non-trivial character over a group, you get 0. So over O, it will be trivial, and so you will just get integral of 1. And the integral of 1 is 1. But if you move away from O, then you will have to integrate non-trivial character. So it will be essentially a sum over a finite group. But the sum of all character values of non-trivial character will be 0. We will do this computation many times next time, or even maybe today a little bit. So, well, this is the key point. So the Fourier transform is well defined at the level of functions. We don't have to go to L2. Now the problem is that we want to compute the Fourier transform of the Gaussian function. But the Gaussian function is not in Schwarz space. Yeah, it is like psi of ax squared, and it never vanishes. So it's not in the Schwarz space. So we have to deal with this minor problem somehow. And again, we will mimic some standard tool from functional analysis. But then we will prove that due to our specific periodic situation, there is no need for this. I mean, we do need some definition. So I will give some general abstract definition, but then it will turn out that there is no need for this generality. Well, maybe another lemma that is as obvious. If you take Fourier transform squared, you get just inversion. And then we set Fourier transform minus f of x is Fourier transform f of negative x. And we set Fourier transform minus check from the dual Schwarz space to itself is the adjoint operator. So it's the dual space. So any operator gives rise to some adjoint operator there. Then by this property, we see that if we restrict our extension of Fourier transform on the Schwarz space, well, inside the space of distributions, it's nothing but the original Fourier transform. So we really defined an extension of Fourier transform from, well, as an endomorphism of the Schwarz space to an endomorphism of the dual Schwarz space. Okay. And now, having this definition, we can formulate the next proposition that consider this Gaussian function. So this is the character of ax squared over 2. And this is an element of the dual Schwarz space. It's a function not compactly supported, but certainly just by, where were we? I forgot. Somewhere I defined the map from, there, functions to distributions. So it makes sense as a distribution on the Schwarz space. And then the claim is that the Fourier transform of this Gaussian function is a certain constant factor times the absolute value of a to the power -1/2 times phi minus a, and the absolute value of this constant factor is 1. So it's very similar to what we had for the finite field, only this factor is, extra factor is present. There was no such factor for the finite field. Okay. So, as I said, you have to define in some sense this Fourier transform. And so what I said before, what I said here, allows us to define this Fourier transform. But then it turns out that this Fourier transform is essentially the same function, and well, there is no need to go to such troubles. So the plan is to compute our integral for the definition of Fourier transform of phi Gaussian function, to compute it on the bigger and bigger compact subsets, balls. So you have O, then I have this maximal ideal P inverse, P negative squared, and so on. And then it will turn out that the Fourier transform integrals will stabilize. And so when you have a ball of radius 1, of radius p, and so on, and from some point on, when you add some extra annulus, the integral over this annulus will be 0. So the integral essentially will be supported at some ball and can be calculated just as is, without going to distributions, but just plane integral. So this is the lemma we start with. For any x in p-adic number, there exists an integer such that for any bigger integer, the integral over big enough ball for the Fourier transform of our Gaussian function is the same as the integral over p to n negative n naught. Just as I said, the integral stabilizes. Then as you go to bigger and bigger balls, the integral does not change at all. So we take an knot such that this given x, over 2, lies in the ball like this. So if we are not over two-adic integers, well, two-adic numbers, then it's just the minimal ball containing x itself. But since we are dealing with squares, two-adic is somewhat special. We need a little bit bigger ball. So we have to check that the integral over the complement, p to the negative n without p to the negative n0, psi of ay squared over 2, psi of xy dy is 0 for any bigger n. So indeed, for any y in the complement, we can find some number k big enough such that the integral over y in p to the k psi over a y naught plus y squared over 2 psi over x y naught plus y dy is 0. And and again, this will follow from the same observation that psi will be a non-trivial character, and the sum of all character values over some finite group will be 0. So then, we will find then we will split our analysis into a finite union of such small balls as here. Okay, and then we will have that psi of a y naught plus y squared over 2 psi of x y naught plus y is equal to psi of a y naught squared over 2 plus x y naught psi of a y squared over 2 plus a y naught plus x times y. Yes, that's true. So, well, maybe assume n equals 1 for simplification. And the left factor can be extracted from the integral. So by our choice of y naught, we have the absolute value of y naught bigger than the absolute value of x, and hence the absolute value of y naught plus x is the absolute value of y naught by the non-Archimedean triangle inequality. Say this is p to the r, define, and r will be bigger than n naught. So now let's take k equals r minus 1. And then we'll have integral over p to the k psi of ay squared over 2 plus y naught plus x times y dy, and this is the integral over p to the k psi of y naught plus x times y dy, since psi of y squared over 2 is 1 for integral y in p to the power k. But as I promised, psi of y naught plus x times y is a non-trivial character on pk. And hence the integral vanishes, and the lemma is proved. And now I have to stop, but the next time we'll continue. And this lemma, once again, allows us to compute the integral most simple-mindedly. Not as a distribution, but just as an integral. And we'll compute this integral straightforwardly and prove what we wanted here. Okay. And then after this, next time, we will prove that in the p-adic situation, the metaplectic extension of the symplectic group does not split, as opposed to the finite field. We'll prove that it really does not split. And to this end, we will compute some integral over non-trivial quaternionic algebra, and we'll see that it's negative. We'll prove that it's negative, and this will guarantee that the extension does not split. Yes? Yes. Dimensional subspace, yes. Mm-hmm.
Why is it finite dimension?
No, it's definition. I say that a sequence is convergent only if all the members of this sequence, all the terms, lie in some finite dimensional subspace. So, for example, if support grows and grows and grows, then it's not allowed. Such a sequence does not converge by definition.
Where did you use this definition? At which point make you go back and define it in this way?
So, well, due to the lemma just proved, we will never need to in our particular study to use this definition. So we first need to, because our Gaussian function does not lie in the Schwarz space, we need to define its Fourier transform somehow. And we just use this huge space of distributions, dual Schwarz space, and define it in there. But then it turns out that the integrals we actually need to compute, they...
So where did you use the convergence? Where do we need convergence?
Well, I need some topological space. The topological space is the dual Schwarz space with this topology. So I just needed it as a black box, so to say, to define the Fourier transform of Gaussian function as an element of some space. This is a huge space. We don't really need it. But first, we only need it as a black box. We need the Fourier transform of the Gaussian function to lie somewhere. But in this particular problem we're dealing with, we don't need any interesting properties of this space of distributions. Thank you. Yes? No, by no means, certainly not. The dual space is a how is it? It does not have a countable basis. It's very huge. Schwarz space has a countable basis, but not the dual space. And